What if we had a table of values like this right here, and we wanted to come up with an equation in the form y equals mx plus b? Well, we've been messing with this a little bit. We know that as x is going up by 1, we see that these y values are going up by 4. So we would know that our slope for a line that would describe these as sum of its ordered pairs would have a slope of 4, but what would be its y-intercept? Because none of these ordered pairs have a 0 for the x. But no problem. We say, oh, we can put a 0 there. Now if that was 0, what would the number be that would have to correspond to that? Well, since going in increasing order of x, as we go up from 1 to 2 to 3, we go up by 4s. If we're going from 3 to 2 to 1 down to 0, we're going down by 4s. So this guy would be 4. That means the y-intercept would be 1. There would be an equation to model that. I don't know why we're talking about that, but hey, let's suppose we have this house. We got this bug light because we got too many mosquitoes. So the mosquitoes flying and they get zapped, you know, it's awesome. And we watch them fry and we get rid of some of the bugs. But this one doesn't kill as many mosquitoes. We got a new model on the market now. It's a rabbit light. That is a rabbit, clearly, okay? So that's rabbit light, and the mosquitoes, they come flying over and they hit the rabbit and they get fried too. So it's kind of like the Bugs Bunny. It's awesome. All right, but anyways, here's the deal. What we have is, let's suppose the first day that we were out there, we realized that kind of at the start we had 5 bugs in the light, and then end of the second day we had 9 bugs, and then we had 13 bugs, and then we had 17 bugs. And it's like, whoa, that looks like a progression. Like every day we keep gaining 4 more bugs each day. Well, now what's happening here is we got this. This is an arithmetic sequence. It's arithmetic because it keeps going up by a constant amount, in this case 4, and we call this the first term, a sub 1, the second term, a sub 2, a sub 3, and then what we need is we need a rule to find for us the nth term in the sequence. Dang, if only we had a rule. Wait a minute. Do you remember this table we had back at the beginning of the problem? There was a reason why I put that one up there. If we look at these as ordered pairs, 1, 2, 3, 4 for the x, and 5, 9, 13, 17, weren't the values going up by 4 every time? And if we bopped back to the 0th value, we knew that the y-intercept was 1. Well, if we was to call this A1 and A2 and A3, that's an A, and A4, then would this be the first, second, third, and fourth terms? If we just went back 1 to give like the 0, the originating term, the 0th term, that would be like the y-intercept. So we'd have a rule where we go through this arithmetic progression. Instead of y equaling 4x plus 1, we would say that the nth term would equal 4 times the number of terms we need plus 1. So we'd have this rule for describing this arithmetic sequence. So that's what we're going to do. We're going to come back here. We're going to say, look, we got this thing going right here, and we have an arithmetic sequence: first term, second, third, fourth, up through the nth terms, and we need a rule. Now, in your notes, you can put this down. Officially, to find the nth term, we can use this formula. Start with the first term in the sequence, add the common difference, which is like the slope. We're going up by 4 every time. Multiply that by the quantity n minus 1. And the reason for that is, if you're going from the first term and you're jumping by a common difference every time to get to the nth term, there will be n minus 1 jumps of whatever that common difference is. So that's why this rule works. Well, now let's see what happens, because what happens is kind of interesting. We start with the first term, which is 5. And we determine that the common difference is 4, and we're going to multiply by the quantity n minus 1. Now let's crank that out. Let's distribute the 4 across here, and we're going to be left with a rule that says to find the nth term, whatever you want to put in for n, we're going to get 5 plus, distributing the 4, we get 4n, and then 4 minus 1, we're going to minus 4. But if we collect these two like terms, look what we get. To find the nth term, you could do 1 plus 4n. Holy smokes, isn't that what we did when we quickly looked at this as if these were ordered pairs, and we went backwards 1 step, like to the 0th term, to say 13 down to 9, down to 5, down to 1. We can get a rule for the nth term by starting at 1, like the y-intercept, and just adding 4 times n. So If you can use this shortcut, I have no problem with that. To me, that shows really good understanding. If you can understand this rule and use it, that's also important. N minus 1 jumps, each of a common difference. Okay, well, let's try another one. Let's see how it might work if we said, all right, let's have a sequence where we start out with 4, the next term is -1, the next term is -6, and the next term is -11. Well, we're going to need a rule to find our nth term. It equals, let's write this up here again, the common difference times n minus 1 jumps. So we're going to start with the first term, which is 4. So we're going to say, okay, we have a rule to find the nth term. It's going to be start with 4 plus, now what's our common difference? To go from here to here, we're dropping by 5. To go to the next term, again, we're taking away 5. And this is a consistent rate of change, again, slope, rate of change. So we see that our common difference is -5. So we're going to put a -5 in for D and multiply that by n minus 1. Now let's clean this up. Distribute the 5, we're going to get a -5n, and we're going to get -5 times -1 is +5. Added to the 4 is a +9. So this is our rule for finding the nth term. But I would say, if we want to do this in a fairly snazzy way, we say to ourselves, every time we go to an increasing term, we go down by 5. If we go backwards each time, we go up by 5. So to go from the first term to the theoretical 0th term, we would add 5, and that would take us to 9. It's like the y-intercept, the 0th term, and then you lose 5 every time you go up n number to the nth term from there. So, all right, so one more thing on this slide right here. Let's do this. If you want a formula for finding the common difference, the common difference would equal some term, like let's call it the kth term, minus the k minus 1 term. Okay, that's really confusing. It just means this. Take a term like this, and so the common difference is going to be that term of -1 minus the term that's right below it, the term that's one term before this guy, which is the 4. So it's -4. -1 minus 4, D is equal to -5. And it doesn't matter which two consecutive terms you find the common difference with, because -11 minus a -6 is also going to be -5. So that's how we get the common difference. Okay, now, what if we have something like this? We have -15, and we have... I think we get this. I think we're okay with that. Let me show you one other thing, a couple more things. How about this? 2, 6, 12, 24. Okay? Now, is this an arithmetic sequence? It's arithmetic if it has a common difference. Well, let's see. To go from the 2 to the 6, whoops, wait a minute. Sorry, pardon me all the pieces. This needs to be a 3. Okay? Now we're going to be okay. This is a 3. Okay. So to go from the first term to the second term, we would add 3, because 6 minus 3 is 3. But what's the difference here? 12 minus 6 is 6. 24 minus 12 is 12. This is not an arithmetic sequence, because when we go from one term to the next, it's not a common difference. It's a difference that's increasing. So we would say, no, we're not going to get a rule for this because it's not an arithmetic sequence. We're going to find out later that it's geometric, that we realize, okay, if there's not a common difference, is there a number we're multiplying? Are we multiplying by a common number called a common ratio? And you bet your sweet bippy. We're multiplying by 2 to get to here. We're multiplying this by 2 to get to this number. And 12 times 2 is 24. So we're going to find that when we multiply by a common number, that's going to be a geometric ratio. But for now, it's like, oh, no, it's not arithmetic because it's not a common difference, so we can't come up with a rule. But there it is. That's an introduction to arithmetic sequences.